Something like that. No. Yeah, like roll your eyes. You're like, come on. Come on. She said it was always like very.
Oh, yeah, always get it. That's like this is sexual abuse.
It's on the same spectrum.
Like you.
Yeah.
You're not.
I do.
Okay, we're going to start test review today. Okay, guys, just going over the calendar here. So we'll have 3 days to review. We'll go to review today, Monday and Tuesday. Okay. Test will be on Wednesday. Okay. I just want to kind of just, flip through this packet here just to kind of show you what we're gonna what's here. We're gonna try to go. I think we'll be able to finish most, if not all, of chapter 1, review worksheet 1, so pages 1 and 2, and then the keys of task 3 and 4. If you want to work ahead, you're welcome to do that. On Monday, we'll do a similar review worksheet. We'll do pages 5 and 6. I will also enter in the grades. I have all the quizzes graded. I just have to enter them into the grade book, and then I'll hand your quizzes back to you on Monday. So we'll do review worksheet 2. This is kind of like a summary of the major topics that we covered. Evaluating limits algebraically versus real number versus infinity, right? Real number, we plug in that whole number first. Infinity, we don't plug anything in, we go directly into comparing degrees. We need to be able to commit continuity conditions to memory. We're going to do some more of that today, but hopefully, seeing it every day, you'll be able to see it enough times where it'll come naturally. You won't have to. It won't take too much effort to memorize. And then IVT, intermediate value theorem. We did a couple of examples when we learned it, but we will come back and review some of those problems Monday and Tuesday. In the past, we would do a quiz over 1.4, 1.5, and 3.5 before the test. So in the past, we would have 2 quizzes followed by a test. But now we only have 1 quiz and 1 test. So, but I still want to provide this in case we have time. We can do some extra practice. But if not, then I may try to hold maybe like a help session on Tuesday, day before the test, like Tuesday morning, going through this review worksheet. But you can also work through this at your own pace. The key is attached as well. I had a morning review for that quiz. Key is attached as well. And then just more practice problems, especially involving piecewise functions. And key is there. And I will do this morning test review the morning of the test. So Wednesday morning, 7:15. You come in, I will work through this. But the key is also attached here, and I recorded a video from last year, so you can also watch that video if you want to work through it before Wednesday. And the last page, page 25, these are the list of test topics for Unit 1. So we need to be able to evaluate limits algebraically for real numbers, for approaching infinity, and for one-side limits. Want to make sure that that we don't get thrown off with the approach for those problems. Evaluating limits algebraically with a hole in the graph. So this means this is topic 2 is more like what you saw in the last quiz, right? If you get 0 over 0, you know there's 3 things that it could apply. Either it's a factoring problem, conjugate, or a common denominator. Okay, and we'll hit one of each today as we review. Looking at a graph, can you identify limits and order pairs, just like how you were able to show on the quiz? Number 4, sketch a function graph given limit properties. So given properties, can you create a graph that has those properties? And you guys did that on the last quiz. Continuity conditions with piecewise functions. We'll definitely look at some of those today. Apply intermediate value theorem. We'll try some of those on Monday. Horizontal asymptotes and comparative growth rates. We talked about these two yesterday. So with horizontal asymptotes, with radical in the denominator, we know there's going to be 2 horizontal asymptotes. The degrees are matching. We just have to do plus or minus the ratio. So in this case, for number 7, what would be the 2 horizontal asymptotes? One would be what? 3 over 5. Close. 3 over 2.5. Square root of 5. So we have to keep that square root in our ratio. Right? So that's one of them. What's the other horizontal asymptote? Yeah, -3 over square root of 5. So it's just, there's only 2. But it is kind of tricky because this graph looks kind of strange and there's split asymptotes on either side of infinity. So we did go over this yesterday, right? Mm-hmm. Okay. And then comparative growth rates, this is where as long as your numerator and denominator are cleanly separate families of functions, we know that your limit is either positive infinity or negative infinity. Okay. And we can definitely review those types of problems Monday as well. Okay, so just to give you a big picture as to what we're going to be working towards as we prepare for our Wednesday test. Okay, so back to page 1. Now, this is set up a little differently than the problems that we've seen. So what we're going to do is we're going to have to figure out which of the piecewise function that we're going to be using depending on where the graph is headed. Okay, so we have to look at the restrictions on the right to determine which piecewise to use, and then once we have that piecewise function filled in, then we can go through our steps. Right, if it's a real number, we plug in, and then we go through our checks. I do want to point out a couple of things here before we start. Is that some of these are connected graphs, but some of these are just ordered pairs, and I want to identify those so that we don't look at certain things when we come up, so that we don't get thrown off by what's being asked of us. So if you look at the first piecewise here, x plus 5, where x is less than 2, is this a connected piece of graph or is it just a point? So this is saying that I want us to show x plus 5, that's a linear graph, everywhere to the left of 2. So that's a straight line with with an ending point, but it's still a connected part of the graph. So anytime you see a less than or greater than, it's going to have to be a connected, or it's going to be some series of connected graphs. So I was going to put graph here as a reminder that the first piecewise is the graph. Now the second, 11, where x equals to 2, that's only a what?
A point.
It's only a point. Okay. I'll talk about the distinction of this in a second, but we're going through the list here. 2x minus 1, this is a what? Definitely a graph. It's just a segment between 2 and 5. Okay, how about 20, where x equals 5? The point. And then x plus 4, where x is greater than 5. That's a graph, okay. Now, what I want us to make sure that we understand is that whenever we're finding a limit, when finding limits, the point does not play a role. So basically, we don't care about a single point whenever we're considering the limit, because limit, we have to, just like how we did on the quiz, whenever I ask you for the limit, you always looked at both sides of the graph and you look to see where the arrows are headed. You never looked at where the point was occurring, even though there may be a hole in the graph. You're looking at your connected parts of graph. So whenever they're asking for limits, we don't want to get thrown off by the points. The points is not going to play a role. You want information around the point. You don't care about the point itself. All right, so part A, limit as x approaches negative infinity of g of x. Now we have we have a series of g of x terms to choose. We have to choose the correct one based off of our location. So which of these inequality gives us values that's headed towards negative infinity? Say it again. So which of these gives us values that's right? X plus 4 is for values that's greater than 5, right? We have values that's in the negative infinity, so that's going to be what?
X plus
X
5.
plus 5, right? Because x less than 2 is consistent with a negative value that's going towards negative infinity, right? Because if you think about x is less than 2, that's the same thing as saying negative infinity, x is between 2, right? This is just another way of writing it, right? So maybe if you see it this way, it's more obvious that we're talking about the x plus 5. So once we narrowed it down, that's the part of the graph that is being talked about is the x plus 5. We're going to rewrite the problem. And write out the expression. And we're going to go through our steps. Now, this is limit approaching infinity. Do we plug in a value? What do we do if we approach infinity? Compare what? Compare degrees. Now, compare degrees, we need a numerator and denominator. I don't see a denominator, but can I put something in the denominator? A 1. So let's compare degrees now. Okay. Numerator has a degree of 1. Denominator has a degree of
1.
0. Right? X to 0, we don't see x to 0 because it's basically just 1. But the numerator, well, which side has a higher degree?
The top.
The top, which means that there is no limit because this value is getting either larger towards positive infinity or towards negative infinity. So we know there's two options, right? It's either positive or negative infinity because my numerator degree is higher. And how do we test? Good. We choose a value that is headed in the direction that we're going in. We're going towards negative infinity. So if I test x equals negative 100 into my expression, the numerator gives me negative, denominator stays positive, right? Well, actually, there's no variable, right? It's just a 1. I put an x to 0 there, but just to compare degrees, but really it's just a 1. The numerator is negative, denominator is positive, therefore negative. All right, number 2, part B rather. Limit as x approaches 2 from the left side of 2. So which of these has values that's a little bit less than 2 headed towards 2?
Oh, the same thing.
Same thing, right? X plus 5. So if you think about values like 1.5, 1.6, 1.7, those are all values that's less than 2. So we know we're dealing with x plus 5. Okay, so. All right, so now we have a real number limit expression in front of us. What's the first thing that we do? Just the 2, right? Decimals, we don't do anything with decimals until we realize there's a vertical asymptote. If there's no vertical asymptote here. We plug in 2, we get a real number. We have our one-sided limit. Okay, part C, approaching 2 from the right side of 2. So what are some values a little bit greater than 2? That's part of our restriction here.
2x minus 1.
Right, so if you think about values greater than 2, it could be like 3 or 2.5 or 2.6. Those are all values that's between 2 and 5, so we use 2x minus 1. Just the whole number, right? Okay, plug in 2, what do we get? 3. All right, part D, limit as x approaches 2. All right, how would you consider this one?
You do either side, can you?
Okay,
Was 5, X was 5.
X plus 5 though.
so imagine you have the graph in front of you, and if I ask you to find the limit, what would you do?
Oh, you'd like do both.
You have to do both sides, right? I gotta pick points on either side of 2, and I want to look at to see where the arrows are headed. So are the arrows headed in the same direction?
No.
No, so this would be what?
E and E.
Limit does not exist, right? So we know what visually it looks like. This is what it looks like from an algebraic perspective, okay? But we should kind of imagine the picture of that. Now, what do you think is a common mistake that students also make?
The same thing.
Oh. I think what I see a lot is students see the 2 there and they say, well, I see a 2 here, so I can just put 11. Okay, but we talked about how a point is not going to play a role. That point is sitting there, but we're talking about the approach. This is going to give us a much better answer, but much better idea of what the limit is than that 11 is going to do. So here, limit does not exist.
If it were looking for 11, it would just say like G and then parentheses 2, right?
Exactly right. Now, exactly. If it was asking for what is G of 2, then you would say 11. Because I'm looking for just a physical point. But anytime I'm looking for a limit, I have to look to see what's happening around that point, not so much the point itself. Okay, part E, approaching 5 from the left side of 5. So think about values that's a little bit to the left of 5. Where does that fall under?
2x minus 1.
Good, right? So think about like 4.5, 4.6, that all falls inside this interval here. We'll choose the 2x minus 1. No decimals in our expression. Just insert the 5. We get
9.
approaching 5 from the right side of 5. So we want values greater than 5. So
X plus 4.
plus 4. Get
9.
9. So is that going to help inform us for G? Okay. Limit equals 9, because the approach from both sides of 5 are consistent. They're both headed towards 9. The order pair is living somewhere else, but we don't care about that order pair. We care about the arrows, right? Imagine drawing arrows on the graph and seeing that they're both headed towards 9. Okay, part H, approaching 6 from the right side of 6.
X plus 4. Yeah.
X plus 4, right? I mean, this is way out past our, it's not even close to 5, so we know for sure it's going to be greater than 5. Okay. Limit is 10. All right, approaching infinity. Which one do we choose for that?
X plus 4.
Yeah, because infinity is greater than 5, and that matches our restriction there. So if we're approaching infinity, what's our strategy?
X plus 4 and then put a 1 underneath.
Yeah, we want a numerator, denominator. If we don't see a denominator, we can always put a 1 there. Okay, we compare degrees. Which side is going to win out? Numerator, which means that there is no limit. However, we have two choices to choose from, either positive or negative infinity. What's our test point?
100.
100. We get a positive over a positive. Okay, questions? Okay, for 2 and 3, we're going to, okay, the direction says use continuity conditions. So we just have to step through continuity conditions, and then everything, it's nice to have that structure for all these problems. You just step through it, okay? But for 2, we're gonna, after we step through continuity conditions, we'll see if it passes or fails. If it fails, we will determine where it failed and identify what type of discontinuity it is. So first things first, we need to identify the point, but before that, we need to find the C value. What is our C value? 3, right? We look, C, X is greater than 3, X is less than 3. That's going to be the focus of our problem. 3 is the point where there could be a discontinuity because they may or may not connect at 3. So we know our C value is 3. First things first, f of 3. All right, which piecewise for that? First one. Okay, what do we get?
14.
14. Keep going because we need to at least get to the second condition before we can make any conclusions. All right, second condition is, does the limit exist? Do we need one statement or do I need 2 statements?
2.
2 statements, because I have different functions coming towards 3. I need information from both so that I can determine whether a true limit exists. All right, so limit as x approaches 3 from the left side of 3. Which one do I choose for left side of 3? Less than 3, right? So x squared minus 2. Separately, limit as x approaches 3 from the right side of 3. These are values greater than 3, so that'll be x squared plus 5. Okay, we'll evaluate them separately. First one we get 9 minus 2 is 7. From the other side, we get 14. Okay. What does this tell us about our limit? Does not exist. All right, one's coming to 7, the other's going to 14. So let's make the full statement that the limit as x approaches 3. Make sure that you don't do it this way, that the limit. Okay. I don't want you to, I want to see that notation. I want to see something between the limit and the equal sign. You got to tell me what expression you're talking about. We'll give it a name. Call it f of x. Yeah. That's the way I want you to write it. Okay. I know this is the way that we say it, but this is not correct notation. We need something. We need to have an expression that the limit is referring to. So do we need to go to the third condition?
No.
We already know what category, right? What type of discontinuity is this? Yeah, non-removable. specified location at x equals 3. All right. What's different about part number 3?
You're looking for a value that will make it continuous, like you're taking it a step further.
Yes. And also, we see the inequality looks different, right? Instead of a left branch and right branch, it's more like a graph and a point, right? Then we may or may not have a hold there, depending on whether that point is filling in. So there's a, right, this is the graph. This is the point. But it seems like some of you guys liked rewriting it to make it feel more straightforward. So I'll go ahead and just do that. Nice to just have everything kind of look similar to each other. So when it says x doesn't equal to -3, another way of saying it is this function is defined for x to less than -3, but it's also the same function defined greater than -3. So if I write it out that way, even though it's we're rewriting the same function over again, it does help us maybe map things out a little bit more clearly. So this feels more straightforward because I see a left region, I see what's happening at -3, and I have something to represent to the right. But the first and third statement is the same thing as this first statement here. It just feels more expanded. Now, we were going to go through our conditions here. Now, this direction feels a little bit different, but it's going to be the same process. It says find the k value that will make the function continuous. So all we're going to do is we're going to just step through continuity conditions. And as we step through it, eventually we're going to come across a point where we're going to have to solve for k or figure out what k is so that every condition can pass. So even though it's a slightly different direction, we're still going to go through the same steps. Okay. All right. So what's our c value?
-3.
-3. Yep. It's always going to be what's in the restriction here. Okay. -3. Our c value. So we want to find f of -3. What's f of -3? That's k. Second condition, does the limit exist? Can I just use one limit? Can I just do one limit statement or do I need two?
You can do one.
Just one. I could use two, but then it'll just be x approaching thing 3 from the left side of the same function as it is from the right side, right? These are the exact same. So we would just be doing the same work for the same problem. So might as well just merge it together and just rely on one statement. Okay. We can merge them into the same statement because these are the same functions. We couldn't do that before, right? Because these are just two different functions. That forces us to have to go through two different limits. So now this is algebraic limit problem. Okay, let's go through our steps. First thing, plug in. Confirm what we're dealing with before we jump to our next step. All right, what do we get? 0/0. Okay, that confirms yes, there is a hole. We can factor, match a common factor between numerator and denominator, reduce, reevaluate. So factoring. Multiplies to be -6, adds it to be 1. You see the hole pop up?
Mhm.
Remove it. Reevaluate. What do we get? -5. Okay, did it pass the second condition?
Yeah.
Yes, okay, so we keep going. So we want all three conditions to pass. What needs to happen if the third condition is to pass? The first and second have to agree, right? The point have to be the same as limit. So if we want to force that to happen, then we have to do what? K must be equal to -5. And just by going through the conditions, we're able to solve for the variable we're looking for. Okay, page 2. Now, 1, 2, and 3 are basically review from the previous quiz, but it's good for us to kind of practice through that. So go ahead and try number 1. Go through your steps, right? Even though it looks like, you know, maybe you're already expecting this to be a certain type of problem, but don't skip that first step. Okay, it's a good, it feels a little tedious, I know, but it's really helps us set our anchor for our problem. Right? We know exactly what we're dealing with, and not going to be accidentally going down the wrong path. Because that first step will give us confirmation. Okay, did we get 0/0? Yes. Okay, so we know there's a hole. Now you can go into your factoring step. Now you're looking for holes that's causing that 0/0. Factor the numerator. X plus 3, x minus 2. The common factor is taking shape, but is it a perfect match? Not yet, right? So what can we do?
You got that -1.
Yeah, either from the numerator or the denominator, either one. But we know that they're almost the same, but then their signs are off by -1. So I just decided to factor that -1 from the denominator. You could have done it from the top, it doesn't matter. But as long as we can factor a -1 out, the signs will change inside the parentheses and we're able to get a match and we can remove that the cause of that 0/0. Okay, we don't want to leave our answer like this, right? We're trying to get down to a number, so reevaluate, and what do we get? All right, try number 2.
Is that an 8 for a 9?
Oh, yeah, so number 2 is kind of hard to see. It's x approaching 9.
Okay.
X approaching 9. Confirm that you have 0/0, and this is where we go through the conjugate method, right? So what do we multiply the numerator and denominator by?
X minus 5 plus 2.
Good. Just change the sign between the root the square root and the 2, don't change the sign inside the square root, right? We only want to change what's between the two terms. Okay, FOIL out the numerator. The goal is to try to get the numerator to show some version of x minus 9, because we know that the x minus 9 is obviously causing that 0 in the denominator, so that kind of gives the hint that, okay, there must be an x minus 9 hiding in the numerator, because otherwise there wouldn't be a 0 over 0. Right, so FOIL out the numerator, but don't do anything with the denominator. Just leave those factors alone. Okay, so we combine, I do want to point something out here. On the quiz, I see some students doing this. This is not a perfect example for it, but I just want to point out that you really want to spend the time and effort to clean up your numerator before you try to cancel anything else. So sometimes I see students doing this where they get to the point and they start matching and pairing and try to reduce when things are not ready to be reduced. So anytime your variable is attached to a minus or a plus, it's kind of stuck, okay? We can't remove it between numerator and denominator. Only after a variable, now if the variable is stuck between multiple terms that are being multiplied, then it's safe to cancel out. But sometimes we just start canceling out and it just throws your answers off. So I just want to continue to remind you that even if things look like they are matching, we're not done with the numerator. You got to just try to go as far as you can before you look for any reducing opportunities. Okay, so once you combine the numerators though, and you can see that the x minus 9 is clearly showing up. So that's going to pair up with that x minus 9 from the denominator. Reduce, reevaluate. Okay, and something else that I saw on the quiz was I saw students getting that value of 4, and then they just let that 4 float up to the top. Okay, so that denominator value is not going to move. It's going to stay in the denominator, and there's a 1 left over in the numerator. Even though it looks like nothing is there, there's still a 1 there. So 1 is going to be in the numerator, denominator is 4, 1, 4. Okay. All right, number 3. Okay. Evaluate first. We get 0 over 0. There's a complex fraction problem. We know we have to spend the effort to get that numerator expression cleaned up, right? And the hint is that you look at the denominator, that x minus 2 is obviously causing that 0 in the denominator, and that's what we're looking for in the numerator. We want some variation of x minus 2 to show up for us to cancel out, but we can't do it yet. That x minus 2 is not ready, right? It's not in the form that we want. So we got to focus our attention on trying to get the two fractions to merge together. So we need to find common denominator, get into one fraction, and then we come back and compare what we have left. So we're trying to turn 1 over x minus 1/2 into, we need to find common denominators. So the common denominator between x and 2 is 2x. And then we got to ask between x and 2x, what has changed? A 2 has been added from x to get 2x. So I need a 2 in the numerator to balance that out. So 2 over 2x is the version that I want for 1 over x. Okay. From this 2 to this 2x, we see that there's a change in an addition of x. So I need to include x with my numerator to keep things balanced. So 1 times x is x. Now that I have common denominators, I can merge them into the same fraction. So now that I have a more suitable version of what I started with, I'm going to make that substitution. So I'm going to take this merged fraction and replace with the original. Now, here, I'll work out the rest. So now, I have something that feels like we're going in the right direction here because the x minus 2 and 2 minus x, most likely there's going to be a relationship between those two that will allow things to cancel out. But that complex fraction kind of getting in the way, harder to read it. So I'm going to bring this x minus 2 up. But if I bring it up, I got to flip it. And now I can let that x minus 2 come up to the top. Once I'm here, I should begin to see some things take shape here. The 2 minus x and x minus 2, they're close. They're not quite exactly perfect match, but just like before, we know they're off by a factor of -1. Factor of -1 from one of them. Get the parentheses to match, cancel out, but hold on to the -1. Then once the whole has been removed, we can reevaluate the limits, and we get -1. Okay, try number 4. Number 4 is similar to what we did with the previous page, where there's a hole and there's a point, and we are going through and solving for k. So number 4 is a problem that we can rewrite if we want to, right? Get that first statement to feel more clear. We know that x doesn't equal to -3 means that function is defined for x less than -3, but it's the same function that's defined to the right of -3. And then go down, step through your conjugated conditions. C value is -3. Order pair is k, right? Upper -3 equals k. Second condition, limit, does limit exist? We look at either side of -3, they're the same function. I can merge them into one limit statement. Evaluate, I get 0 over 0. So a factor, right? So factoring, a times c goes above, b goes below. Two numbers that multiply to be -6 adds up to be 5, 2 and 2. So what two numbers multiply to be -6?
6 and -1.
6 and -1, right? 6 times -1 is -6, 6 minus 1 is 5. Factor, we got to deal with the 2 in the denominator, so 6 over 2 is 3, and -1/2. Pull that 2 in front, and I get x plus 3 and 2x minus 1.
Then the bottom is going to be x plus 3x minus.
Good. Denominator, we can make it x plus 3, x minus 3. Clearly, there's a hole, just like what we suspected. Remove the hole, reevaluate, And we get -7 over -6, which is 7/6. It passes the second condition, so we keep going, right? We haven't solved for k yet. So now, what's the third condition?
It has to equal.
Good. The first result from the first condition has to match the result of the second condition if I want this to be a continuous function. So that forces k to be equal to 7/6. Okay, we'll pick this up on Monday. If you want to work everything, if you want to work ahead, feel free to do that because you do have the key. But just pace yourself, whatever it takes, for you to feel comfortable for Wednesday. Okay, come up and get your phone.